Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electrical machines. So in this video we are going to take our discussion forward related to the basic concepts related to the property of magnetic effects, the electromagnetism. So in this video we are going to discuss about magnetic dipole. Okay, so this is related to why various materials they possess magnetic properties, why and how much they possess. So we'll try to explore the reason behind that. So before going into all that, magnetic dipole. So a magnetic dipole basically it consists of two unlike magnetic poles of equal pole strengths but opposite in nature, separated by a certain distance. Okay, so the fixed distance they are separated by is given by 2L, that L vector, and the pole strength, which has the unit of ampere meter, they are of equal magnitude but opposite nature. Okay, south north as it is. So here, so the distance between the two poles, 2L vector, is called as the magnetic length of the magnet. So the magnetic dipole, important parameter associated with it is the magnetic dipole moment, capital M vector, which is the product of the pole strength multiplied with the magnetic length and has units of ampere meter square. So it is similar to the electric dipole that we have discussed in the electricity and magnetism discussion. In that playlist you can check out the electric dipole concept. So the magnetic length is basically a vector, as it is expressed 2L vector, and it is directed from the south pole to the north pole. Okay, so this is the magnetic dipole. There are a lot of other concepts related to it. I'm not going into all that. I'm just sticking to what is required in our discussion related to electrical machines, because there are a lot of things associated with each of these concepts that we're discussing. We are only focusing on those aspects that are required for our understanding of electrical machines. So we are not going unnecessarily, going into detail about all that. So current loop as a magnetic dipole. Okay, so this is where it we are trying to link it with electrical machines. Okay, now let us say we have a plain loop of wire, circular loop, and current flows through it in a certain direction. Now we know that a current carrying conductor or a current carrying wire, it behaves as a magnet. Magnetic effect of electric current was to its discovery. So this is the whole principle of electromagnetism. And when the direction of the current is reversed, the magnetic behavior is also reversed. The magnetic lines of force, the magnetic field direction, it also changes. We have discussed it in the first video. Okay, the magnetic field, magnetic flux, all that. So how this plain loop of wire can behave as a magnetic dipole? Okay, so here we have this plain loop of wire carrying current. Now if someone tries to view it from the top, okay, from the top, if one tries to view it, they will see that the current is flowing in anti-clockwise direction, okay, from the top. And if one tries to view it from below, then it will seem as if the current is flowing in clockwise direction. From the top anti-clockwise, from down clockwise. So the upper side, the upper face of this plane loop, it behaves as the north pole, and the lower phase, it behaves as south pole. Okay, this. Now, the current carrying loop, this, behaves as a magnetic dipole. Okay, and the magnetic dipole moment of this current carrying wire loop is given by the product of the current I and the area of the loop. Okay, the area of the wire loop. And this is for a single turn wire, and when there are n turns, multi-turn wire, if there are more number of turns are there, then it is NIA. Okay, this. So why this discussion is important? Because electrical machines, we have wire loops wound over core and current flows through it. So there, this whole concept of magnetic dipole will come in mathematical calculations and expressions. So that's why at that time I will simply be referring to this video so that you understand why that thing happened the way it happened. Okay, why the mathematical expression was expressed in terms of magnetic dipole moment, how the term magnetic dipole moment came into the picture. So at that time you will have no confusion. So you'll simply watch this video, or if you remember, then you will understand, okay, this is the whole thing. Okay, so this is the current carrying loop behaving as a magnetic dipole, and this is the magnetic dipole moment. Another important thing, important concept associated with it, is an atom behaving as a magnetic dipole. Now we all know, according to the atomic theory, the electrons, they revolve around the nucleus in well designated orbits according to Bohr's atomic theory. So the atomic movement, it gives rise to its behavior as a magnetic dipole. So we know that a current carrying loop, it behaves as a magnetic dipole. Now when an electron moves around the nucleus with a certain velocity, it is similar to a loop of wire carrying current. Okay, now this movement of the electron, it gives rise to current flow in the opposite direction, because we know current flows in the opposite direction to that of the movement of the electron. So as a result of this flow of current in the around the the orbit, it gives rise to a similar kind of a situation to the current carrying loop. Okay, the flow of electron around the orbit, around the nucleus in the orbit, specific orbit, it gives rise to flow of current, and this is a similar situation to this current carrying loop. As a result of this, because of the flow of current, this current opposite to the movement of electron in the opposite direction, there is two sides of the orbit, the upper side and the lower side, they behave as two different magnetic poles. Okay, so here the upper face, it acts as the south pole, and the lower face, it behaves as north pole. Because the electron, it revolves in anticlockwise, so the current will be in clockwise way. So this gives us the atom as a magnetic dipole. So that's why I introduced this thing first, current loop as a magnetic dipole, then I introduced this. Okay, flow of electrons or the movement of electrons around the nucleus in specific orbit leads to flow of current in the opposite direction, similar situation to that of a current carrying loop, and this gives us the atom as a magnetic dipole, that behavior. And the magnetic dipole moment for the electron, or the orbital magnetic moment as it is called, it is given by this expression, NEh by 4 pi m. capital M, the orbital magnetic moment, it is given by NEH by 4 pi m, or N mu b, where mu b is EH by 4 pi m is the Bohr magneton. Okay, EH by 4 pi m, mu b. Okay, the N is not there, it is simply EH by 4 pi m, simply EH by 4 pi m. So this is the Bohr magneton. Here E is the electronic charge, H is Planck's constant, m is the mass of the electron. So this is the reason why certain materials, they have or they possess magnetic properties in varying degrees that leads to, you know, classification of magnetic materials as paramagnetic, diamagnetic, ferromagnetic. So that is for a separate video. I don't want to introduce all those things here. So at that time, this concept of the atom as a magnetic dipole will come into play. Okay, so this is about magnetic dipole. We have discussed basic concepts related to that, current loop as a magnetic dipole, and atom as a magnetic dipole. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.